So one of the really important concepts to understand in this section is something called Le Chatelier's principle. And it's actually pretty easy to know what's going to happen. But let me give you the definition and I'll show you how this applies to our system of cups and colored water, okay? But basically this is what Le Chatelier's principle says, is when a system at equilibrium is challenged, it responds to minimize the challenge. Okay, so what does that mean? Well, a challenge to a chemical reaction is like a change in the temperature or changes in like gas pressures or changes in concentration. Okay, so these are the types of challenges that we see. We see concentrations, that's primarily what we'll be talking about in this chapter. But it could also be for like gases, it could be pressures. And really, pressures of gases, for the most part, represent their concentrations and temperature. So think about like our little 2-cup experiment, right? Oh, zoomed way in too far. Here we go. And this is not something we did, but I think you'll get it, right? So this is liquid here. And let's say it's at equilibrium, so it's kind of like this. And it doesn't matter, actually, make the glasses really different size, because I think you realize by now it's not the size of the glass that matters. It's the levels of the liquid, right? So then I'm going to put my tube in here like this. Okay. And if you've ever watered a field, they have things called siphon tubes. It's the exact same kind of principle that is in operation there. They just put water in one side, and you hang a tube over a trench, and it drags water from the supply side to the furrow side, and the water goes down that way. But anyways, yeah. So if you have this situation, right, this is at equilibrium. The left side and the right side are balanced, right? So now what I'm going to do is I'm going to pour in more water. So add more water, right? So you tell me, you think about what's going to happen, but I think you know, right? I add more water and I'll stop. Then what'll happen is it's going to shift this way, right? The water, the water in this side of the tube is going to start moving towards the right and filling up what's over here. Now, if I had other things than this liquid, right, those would go over the tube as well. So if I had 2 different liquids, let's say I had water and alcohol, and I made a homogeneous mixture here, and this is just water on this side, they would still come to an equilibrium. But if I added more water on this side, it's going to drag that alcohol as part of the solution through the tube, and it'll end up over here. Now think about this. If I added more water on this side, so this is the situation. If I add over here, what's it going to do if I add it to the right-hand side? Well, then what it's going to do is it's going to go this way. And this is what we mean. This is what Le Chatelier meant by saying when you have a system and you challenge it, like you add a reactant or you add a product or you do something to put it out of equilibrium, the system always responds in a way to reestablish equilibrium. Eventually, in the water situation, the levels get to be the same. Same levels, okay? So this could be like A and B, and this could just be A. And this could be C, and this is my reaction arrow like that. I'm adding A, I've got a mixture of A and B, and it's going over to the right-hand side, right? So I want to show you how this works, though. A way to think about it, right? So I'm going to use this that arrow or this arrow, that's my challenge. So I'm going to go like this, and then we're going to try to predict what's going on. And I always draw a column underneath here, and I'm going to say I'm going to add more A. That's my challenge. And then you would have thought, well, it's going to go to the right, like that. So as a result, what's going to happen is C is going to increase. That's what this arrow means. And then B is going to decrease because it's getting dragged over to the other side, right? So you can predict what's happening to everything in the solution if you know what the challenge is, you know which way the equilibrium is going to respond, and once you know that, you know the direction to change for everything else. So this is the first thing. You have to find the challenge. That'll be part of the question. If you increase such and such, right? So now I'm going to get back to this because I have to make one qualification to what I said, but this is the idea how this works. So on first glance, this is the first thing I do. Look at the challenge. The second thing I do is I go like that, right? I decide which way the reaction has to shift to get back to that balanced situation. And then I can predict what each of the things is going to do. I would predict that this goes up in concentration, and I would predict that this goes down in concentration. Now, the one thing you have to be careful of is after you're thinking about all that, just think about what's solid and what's aqueous, and liquid and aqueous, and this is a solid. So in fact, right, remember what I said, what this means is B is getting used up, but its concentration remains the same because it's a solid. That's this argument that we're making up here. Like as I use up this block of material, that could be B, its concentration remains the same. And what we're talking about in this scenario is concentration. Let's do one more. I'll do it in a different color. Let's say I make C. Let's say make A go down. Then I'll do one with C. So that's the first thing. What's the second thing that you do? The second thing is you predict the direction of the arrow. Right? And then you predict that C will go down and B will go up. So there'll be more B, but the concentration of B remains unchanged, right? So there'll be more reactant B because I pulled some A out. We'll do one more, and I'll do one dealing with C. Let me draw lines in between here to make it clear. Let's make C. This is my challenge again. I'm going to make it go up. All right? So what's going to happen? Well, because it's like pouring water in the right-hand side, because I added water to that right-hand side, it wants to shift towards the left. So the shift is going to be in this direction, right? So the first thing I do is always the challenge. I identify what's being changed. I identify which way the reaction is going to shift. And that means B's got to go up, and so does A. Because the reaction is going to be going to the left-hand side, then both reactants will be going up. All right, so I'm going to show you this one. These are more complicated in some ways because they're not dealing directly with concentration. What Le Chatelier said about pressures is, and this you have to understand how this experiment is done, okay? But he basically said when you decrease the volume, of a gas reaction, the reaction shifts to the side with fewest moles. And the opposite's also true. If you increase the volume, it shifts to the side with more moles. So what did he mean by that, right? Well, the way this experiment is done is you can have a piston. That's a favorite thing of chemists. You can have a piston. You can think of it even like a car cylinder, like a piston that way, right? Uh, but we have this reaction sitting in here, and if I decrease this volume, right, that means it's increasing pressure. You think about how that's called compression, right? When you have a piston and it drives into a cylinder of any type, the volume is going down, but inside that piston, the pressure is going up. And then you can release that pressure by bringing the piston up. In fact, if you take the piston and you pull it beyond, right, then the pressure goes down on the inside. So Le Chatelier has really said this in terms of pressures. If you increase the pressure of a chemical reaction, it'll go to the side with fewest moles. Or if you decrease the volume, it's the same thing. Or if you increase the volume, it'll go to the side with more moles. So, how do I know which side has more moles, right? You just look at these numbers. There's 1 here. You didn't write it. And there's 3. So there's 4 moles on this side. And I have 2 moles on this side. And I'm going to draw this like this. And we'll predict which way this reaction shifts when I change the volume or change the pressure, okay? So, if I make the volume smaller, it's going to go to the side with the fewest moles. So this is smaller volume, or higher or larger, if you want, if you want to put it that way. Larger pressure, higher pressure, I should probably say. So, we'll put it all like this, and we'll do the other one below it. Excuse me. If that's the case, then what happens is going to shift this way, and so this will go up, and these will both go down. Right? High pressure goes to the side with fewer moles, or smaller volume will go to the side with fewest moles. Now, if I do the opposite, let's do low pressure. Then what it wants to do is it basically wants to go to the side that will fill it up better. It's going to go that way. And when it does that, then the left side goes down and the right side all goes up. And in fact, this is the way that they initially made fertilizer back around World War II. Ammonia was one of those things they needed to make. And so these 2 scientists, let's see, what were their names? I want to say Haber. It was called the Haber Process. I'll have to look that up sometime. But anyways, they figured out if you increase the pressure of this reaction, that's what they're doing here, you could get more moles of ammonia out, and ammonia is a key ingredient in making fertilizer. It also turns out it's a key ingredient in making bombs, and so it ended up being like real useful for that too, unfortunately. All right. The last topic to cover is the effects of temperature. So if a reaction is exothermic, then the way we think of temperature is we think exothermic means releases energies from way, way back, 2 weeks ago, way, way back. When it releases energy, it makes its surrounding hot. If it's an endothermic reaction, then it absorbs energy and it makes its surroundings cold. So, the way a chemical reaction will shift depends on whether or not the energy is a reactant or product. So if you take a reaction of A goes to B plus energy, an exothermic reaction, and my challenge is temperature. And if I make the temperature go up, then what happens in this reaction is because the energy is over here, it's like increasing increasing temperature is increasing the energy, it'll shift in this direction, and then B goes down and A goes up. Now, if I have the second situation, I have an endothermic reaction, and I increase the temperature, the challenge, right, is I'm doing this. I'm increasing temperature. That's the same as increasing the energy. So if I increase the energy, it's going to shift to the right, like this, and then A has to go down, and B has to go up. So the energy, if you think about it like it being water, if I'm adding water to the left side, it's going to go to the right. If I'm adding water to the right side, it's going to go to the left. Similarly, I could take water out, or I could take energy out, right? So if I cool it, and it's exothermic, and I take energy out, that means this will be going down, right? And that means it'll go towards the right, and you'll get more product. So that's kind of a summary of Le Chatelier's principle. I really encourage you to sort of do it like I did it here, or like I did it up here with the arrows up here. Because it really helps clear up like which way things are going to go. But if it's easier for you, just think back to the cups with the water in it and think, oh, am I adding from the reactants or subtracting from the reactants? If I'm adding to the reactants, it'll shift to the right. If I'm subtracting from the reactants, it shifts to the left. And you can say the same but the opposite about the products. If I add to the products, it shifts left. If I subtract from the products, it shifts to the right.